Welcome to everybody. My name is Enrico Scala, and I'm going to talk about numeric planning problems and new techniques that can be exploited to scale up on this class of problem. This is a work done with Alessandro Saetti, Serina, and Alfonso Gerevini. Numeric planning problems are deterministic planning problems in which you can express numeric state variables. And these numeric state variables can be used in the definition of quantitative constraints that you can express at the level of preconditions of the actions or goals. Action effects can include also numeric transitions through which you can update these numeric variables as you apply actions. This representation is useful when you want to encode in your planning problem resources, coordinates, or any other quantitative aspect you may be interested in modeling. When you express this information explicitly, you can exploit it for reasoning much better, something that it's difficult to do if you use a pure classical planning approach, which basically will hide your numeric structure. A common and somewhat effective way to solve numeric planning problems is using forward state space search. However, the effectiveness of such an approach depends on how well the search over this state space is guided. There are mainly two approaches to this problem. One is using a relaxation based on intervals, and the other one is a relaxation based on decomposing subgoals, which is extension of Hmax, Hshad heuristics devised for classical planning. In this paper, we want to better understand this relaxation and especially understand how this can be better integrated into the search. We devise a new notion of relaxed plan that we call multi-repetition relaxed plan, new helpful actions, and a notion of up to jumping actions, which is a particular device that further capture some structure in the numeric planning problem. We focus on what are called the simple numeric planning problems, which are those in which only increase and decrease operation of a constant are possible and all the constraints are linear. A multi-repetition relaxed plan is formally a set of pairs, each encompassing an action and an action counter. This multi-repetition relaxed plan is defined recursively, taking the best achievers from the subgoaling based relaxation. It can be computed using the recurrence equation that you can see on the slide, and this equation makes it clear that when the condition at hand is a numeric condition, this formalization can directly exploit the numeric structure of the problem by explicitly mentioning how many times an action has to be applied, and this is what goes into the pairs as an action counter. The multi-repetition plan heuristic is not the sum of all the actions in the plan, but is the sum of all the action counter in the plan. When there is the pairs sharing the same action, we take the maximum among those pairs with respect to the action counter. In this example, you can see how a multi-repetition plan can be computed. This is an example involving a sailing boat that has to reach two areas, and it can perform the action displayed on the right-hand side of the picture. The MRP for this problem involves actions with multiple repetitions, and if we compute the heuristic on using this multi-repetition plan, we get actually the optimal cost of this problem. And the optimal cost, the fact that we get the optimal cost is due to the fact that we can capture that there is some sharing or contribution of the actions towards different goals that are different but are related somehow. We also define a notion of helpful action from this relaxed plan, which is pretty much the same that you get For classical planning, here the difference is that when we establish the achievers of a sub-goal into the relaxed plan, we can reason on the numeric structure of these sub-goals. So we get the helpful actions that we say are possible achievers of these sub-goals. As you can see from the example, with respect to the IBR helpful action mechanism, in this example we only get the green actions, which are the actions that can eventually satisfy those constraints, while the IBR, because it looks at state variables decomposition, not numeric condition decomposition, will get also the brown actions there, which are not actually helpful at all for this problem. Always with the idea of better exploiting the structure of the problem, we define the notion of an up-to jumping action, which is basically a pair action plus the action counter. These up-to jumping actions are similar to regular action, that they can be applied when the preconditions are satisfied, but the effect of this up-to jumping action depends on the state in which the action is applied. We execute this action when this action is deemed executable. Its execution goes up to the point in which either the number of repetitions is saturated or the preconditions of the actions are not satisfied anymore. We take these actions from the relaxed plan by focusing on those, in this case minimizing the action counter. This is to have a finer jump into the state space. And as you can see in the example, here we have these two up-to jumping actions that let us jump directly into the region of interest. We performed experiments using a greedy best first search algorithm, and we compared the three different configurations. Only the heuristic that we have proposed, the heuristic plus helpful action pruning, so we branch only over helpful action, and the heuristic plus helpful action pruning and up-to jumping actions. So we add up-to jumping actions into the frontier by using the semantics that I described you before. We compare performance against the HAD and the metric FF planner, and we use domains from previous international planning competitions and more recent domains. We test coverage, runtime, and plan length. As you can see from the experiments, all the new techniques scale better than the baseline, and this advantage is more pronounced when you equip the search with helpful actions and up-to jumping action. On the right hand side you can see the number of expanded nodes between HAD and the best configuration that we have, and as you can see the number of expanded nodes, it's reduced in a way quite uniformly over all cases that we tested. This can also be explained by looking at the coverage, the increase of coverage, which is well spread over all domains that we have used. Regarding the cost of the solution, we observed that there is an increase of the plan cost when we use helpful or up-to jumping action, and this was somewhat expected, but this is limited in some problem, like in the sailing problem or in problems where there is a less pronounced numeric structure. The techniques that we have seen in this paper are new ways to exploit the structure of numeric planning problems. In particular, the technique that lets us jump many steps in the future through what we call up-to jumping action seems to be a very promising technique, and we want to see whether this can be applied in other contexts, for instance, in the optimal planning settings. Thank you.